Dr. Key is originally from Langley, Washington, on Whidbey Island. She's an assistant professor at of physics at the University of Washington, Bothell, and growing up, she wanted to be a wide receiver for the Seattle Seahawks. But she was never drafted. So instead, she became an astrophysicist, pretty typical, and plays ultimate frisbee. Let's welcome Dr. Key.
Thank you. Good evening. It's great to talk to all of you tonight. Let me see if I can get that video to play one more time. Great. Okay, so from the very small to the very big. 100 years ago, Albert Einstein predicted that accelerating masses would create ripples in space and time that travel at the speed of light. We call these gravitational waves. They are created by very massive objects in our universe, such as black holes, orbiting around each other. When they collide, they create a lot of gravitational waves and collide to make a bigger black hole. So that's the animation that we just watched. And this animation was created to show what it would look like if we were close enough, but a safe distance away, to two black holes as they collided, making gravitational waves, the very first gravitational wave signal that was ever detected by humans. The experiment that made this detection is called LIGO, the Laser Interferometer Gravitational Wave Observatory. There's a detector in Livingston, Louisiana, and another detector in Hanford, Washington, just over the mountains. Has anyone ever been there? Everyone should go visit in the Tri-Cities area. You can visit LIGO. These are laser interferometers. We just learned a little bit about lasers. This is another great use for lasers. LIGO uses lasers, a laser in the central station there, and then a beam splitter that splits the laser into two parts and sends it down these long arms. They're 4 kilometers, about 2.5 miles long. They're long vacuum tubes, some of the largest vacuum systems in the world. Then there's mirrors at the end of those long arms that reflect the laser and bring it back to the central station to measure very, very precisely the length of the arms to tell if gravitational waves have passed through the instrument and Earth and us, changing the length of those arms by just a tiny bit. Einstein didn't think that it would be possible to detect gravitational waves. And indeed, it took 100 years of human ingenuity to build these instruments to make the very first detection of gravitational waves. And we can actually hear the gravitational waves in the LIGO data. It's called a chirp. You can sort of hear a little bit of the frequency sweeps up. You can also see it in the graph there. So that is what it sounds like when black holes collide. Maybe not what you were expecting, but it is actually what we calculate and predict for black hole collision, and indeed what we heard on September 14th of 2015, which was the very first detection of gravitational waves. Then In August of 2017, we got a new kind of signal. This one, which also sounds a little bit like a chirp, so you sort of recognize the sound, came from, instead of two black holes colliding, from two neutron stars colliding. Followed by, in this case, when two neutron stars collide, it turns out there's some messy astrophysics that happens, and there's a bunch of light that is also created. When black holes collide, it is still dark, but when neutron stars collide, it makes light. And so a NASA satellite called Fermi has a gamma ray burst monitor, and just after we detected the gravitational wave signal from two neutron stars colliding, the Fermi satellite detected a gamma ray burst. Gamma rays from a distant galaxy. This joint detection set off a worldwide search for the galaxy where those two neutron stars collided. Now it turns out that gravitational wave detectors and gamma ray burst monitors are not very good at telling what direction the signal came from. But working together, the two LIGO detectors, a third gravitational wave detector in Italy called Virgo, and the gamma ray burst monitors on Fermi and Integral work together to find the portion of sky where the signal came from. Then some telescopes in South America searched the sky, looked through all those galaxies, and found the host galaxy where there was a bright new star that we now call a kilonova from the two neutron stars colliding. So this is the first, what we call multi-messenger astronomy detection with gravitational waves and light. And this kilonova was studied by pretty much most of the astronomers on Earth, with telescopes on all 7 continents, and astronomers all over the world observing this kilonova event and the light and afterglow that came after the collision. So LIGO is now probing the population of black holes in our universe. There have now been 10 black hole collisions that have been observed by LIGO. You can see them up on the top here, as well as the neutron star collision at the bottom there. When those two neutron stars collided, you can see the little arrow points up to a little question mark. We're still actually not sure if after the neutron stars collided, if they collided to form a black hole or a neutron star. And we don't have enough data to be able to tell which one it was, so we hope to detect many more of these kinds of signals to be able to start answering these kinds of questions. And we all now live in the era of gravitational wave astronomy. This is a totally new kind of astronomy. We'll be exploring pairs of black holes. We don't know a lot about black holes out there in the universe, so this is a great way to do it. The LIGO detectors right now are being upgraded and will turn on for our 3rd observing run this spring. So keep an eye out for more detections coming up later this year. We really are lucky to be living in this time when there's a totally new way for astronomers and humans to be able to explore our universe. So thank you.